Welcome back. We will now proceed to consider the second question in the 2023 paper 1 on mathematics. So we've had the first one. I'll put a link to that in the description so you can go ahead and watch that and then proceed with this. Okay, so let's see what is required of us in this problem and how to go about it. So it says let T1 and T2 be two distinct common tangents to the ellipse E given by x squared over 6 plus y squared over 3 equals 1 and the parabola P given by y squared equals 12x. Suppose that the tangent T1 touches P and E at the points A1 and A2 respectively, and the tangent T2 touches P and E at the points A4 and A3 respectively, then which of the following statements is or are true? Again, like the first problem, this also may have up to 2 or 3 correct options. Okay, so we'll find out what those options are, which of the options are correct as we proceed. So what do we mean by this? Firstly, we have an ellipse to deal with. We also have a parabola to deal with. Common tangents. We know that a tangent to a curve simply touches the curve at one point. So we will find a tangent that touches this curve and at the same time touches this curve. That is a line that is tangent to the ellipse and at the same time it is tangent to the parabola. That's what is meant by common tangents to this ellipse and this parabola. So how do we go about that? So firstly, we can see that the equations here, this equation of the ellipse and the equation of the parabola have been given in their standard forms. So what do we mean by that? So let's quickly recall that here. For equation of an ellipse in standard form, when we have an ellipse, the equation of the ellipse in standard form is given by x squared over a squared plus y squared over b squared equals 1. So where in this case, A will be the length of what we call the semi-major axis and B will be the length of the semi-minor axis. And of course, it can also be that B is the length of the semi-major axis and A is the length of the semi-minor axis. It depends on which of these two is greater. Okay, it depends on which of A and B is greater. Okay, so this is for an ellipse, which will generally be in this form. That is, the ellipse whose equation is this would look like this. When we draw this on our xy plane, this is the x-axis and this is the y-axis. So this is centered at the origin, so we'll have something like this. Okay, for the ellipse, we'll have something like this. So these points will be our minus a. So this is on the x-axis. So we have this, which is a. So this is going to be minus a at this end and plus a at this end. So, and for the y-axis, the denominator of this is b. So this is going to be plus b at this end and minus b at this end. So this is that equation of the ellipse. So we also know that, or we expected to know that when you want to get the equation of the tangent to the ellipse, okay, in the equation of the tangent to the ellipse is given by, and now we can have different forms for the equation of the tangent to an ellipse. We can have it in terms of the points. Let's say we want to get the tangent to this ellipse at the point x. In that case, at the point say x equal to x1, we'll have to find out what the equation is of that tangent. So let's say this is that tangent. We'll have to find out what that equation is in terms of the point x1. So for that case, it depends on what exactly we know about the tangent also. So if we know the point where they intersect, we will find out what the equation of the tangent will be using the point of intersection. That is the point where the tangent meets the or touches the ellipse. But we don't have that information here. In this case, we only have the equation of the ellipse and we only know that the tangent is common to both this ellipse and this parabola. So that means the only thing we are sure of is because The same line will touch both the ellipse and also the parabola. We're going to draw that shortly. Then we are sure that since it is the same line that touches both of them, that line will have the same equation, and of course that line will have the same orientation, which is defined by its slope. So the slope will be the same for the line because the line will touch both of them. So because of that, it is best we use the slope form of equation of the tangent to the ellipse. Okay, so we say that the equation of of a tangent, equation of a tangent of slope m, equation of a tangent of slope m to the ellipse, that is the ellipse with this standard equation, is given by, so we know the tangent is a straight line, and equation of a straight line is given by y equals mx plus c. Okay, so in terms of the slope, if we know the slope or we can relate the slope to some other quantity, then we'll make use of this form. So this is going to be given by y equal to mx, okay, then plus or minus the root of a squared m squared plus b squared. So that is the expression for the equation of a tangent of slope m to the ellipse. Okay, so a will follow from the equation of the ellipse, this standard form of the equation. That's where we get our a. So m is that slope. Okay, we don't know what that slope is, but we know we can relate it to that of the parabola, because the slope in this case that we're interested in, sorry, the tangent in this case that we're interested in is a common tangent to both this ellipse and this parabola. So they will have the same slope at the end of the day. So we'll come back to make use of that information as we proceed. Okay, but for now, we have this. This is enough detail for us to solve the problem as far as the properties of the ellipse are concerned. Okay, so now let's quickly discuss those things we need as for the case of the parabola. So we know that the standard form of the equation of a parabola, standard form of the equation of a parabola. So for equation of a parabola, we say that it will generally be given by y squared equals 4ax. Okay, that is actually the form that we're given here. Okay, although we don't have a here, but we can of course write it in this format so that we can get a. So what is the meaning of this, and what will the parabola defined by this equation look like? Okay, so we know that this is the parabola. The parabola will look like this. We'll have x here, and this is our y-axis. So when you see something like this, you should already know that this one is squared. So because this one is squared, first and foremost, the way it is now, if x is 0, y is also going to be 0. So that tells us that the parabola, whatever shape this represents, is going to pass through the origin, because when x is equal to 0, y is equal to 0. Another thing to notice here is the fact that y is squared. So because y is squared, x will always be positive. So for instance, if you imagine that you make x the subject here, x will be y squared over 4a. So this represents a situation where x is always positive. So that means the parabola will be facing this x direction. So the parabola, that means that the curve will not show anywhere where x is negative. We know that x is positive to this side, x is negative to this side. But because whatever y is, it has to be squared, then y can be positive or negative, and whether it is positive or negative, x will always be positive. So this is a parabola that faces the positive x direction. So we're going to have something like this. Okay, we will have this, of course, for a positive a. Okay, a has to be positive for that. Okay, so we can have this to be all negative. For instance, it can happen that x is also always negative. If it happens that a is negative, so that means that will be facing this direction. Okay, but we know that this y squared is always positive, so the sign of x will be determined by the sign of a. So if a is always positive, then this will face this direction. If a is always negative, then this will face this direction. And if it happens that it's meant to be a parabola that faces up, that means it will be in the form something like x squared equal to 4ay. So that in that case, if a is positive, y is always positive and that faces up. And if a is negative, y is always negative and that faces down here. So that's how we know the orientation of the parabola from this equation. So this is the standard form that aligns with the equation that we are given here. It says y squared equals 12x. So we can easily write that in the form y squared equals 4ax, and our a would be then positive. So because of that, we expect that parabola to face the positive side of the x-axis as we have sketched it here. Okay, so that is that about that standard form of the equation. So what else do we need for the parabola? The we also need its equation, the equation of a tangent of slope m to the parabola. What is that equation? So we say that equation the equation of the tangent or a tangent of slope m, the equation of tangent of slope m to the parabola, that is the parabola defined by the equation up here, is given by y equal to mx, y equals mx plus a over m. So this is also in terms of the slope. So these are the equations that we need to have in mind in order to solve these problems. These are the equations. So this is the standard form of equation of a parabola. So of course, A here tells us this distance, okay, to the focus. So this is the focus of the ellipse. So from this point to this point is A. So that is it on the x-axis. So this is going to be A comma 0. Okay. So that is the idea for this situation. And we have the standard form of equation of an ellipse. We know that we can easily compare that with the given equation and find out what A and B should be. And we know this is the equation of the tangent of slope m to the ellipse. So these are the four equations that we need to understand here so that we can solve this problem correctly. Okay, so let me have an additional page. Let's have an additional page to this. So let me know in the comments if you would like to know how this equation came about. But let me quickly mention that you should know that the slope of the tangent to a curve at any point is given by the derivative of the equation of that curve. Okay, so basically this slope is given by the y, the x. So you can differentiate this implicitly and obtain the slope m equal to the y dx to give you the slope at that particular point. And of course, this will be in terms of x and y. Then when you get that, you should try to write x in terms of m and also write y in terms of m by making use of this whatever result you have here and also this equation. And when you do that, you can then use that result to obtain this equation. We know that the equation of a straight line, when we have a given point on the line, let's say we have the point x1 and y1, and we know the slope of the line to be m. We know that the equation of that line will be given by y minus y1 divided by x minus x1 equal to m, because the slope of the line is the change in y over change in x. So this will help us get the equation of the line because this will hold true for any points x comma y on the line. So from this we will generally have y minus y1 equals m into x minus x1. So with this we can simplify further to have y to be equal to, when we open up this bracket, mx minus mx1, then when we move this minus y1 to the other side, it becomes plus. So this will be y1 plus mx1. So we can then use the expressions we will have obtained from here for x1. From here, when we have m in terms of x and y, we'll make that x, okay, be in form of x, in form of m, and also make that y be in form of m. Then we can bring that here, okay, substitute it so that we will have this expression. So it will be completely in terms of m, okay. So we have y is equal to mx over mx plus a over m. So that's how we came about this. Of course, it is not advisable for you to begin to derive that in the exam, or you're expected to have known this already. You should already know these expressions and what they look like in terms of the slope. Okay, so if you already know that, then you don't have to go through this process. So if you would like me to show how this came about, you can let me know in the comment section so that we will have another video on that. But for now, we will proceed with these equations and go ahead to solve this problem. Okay, so let's see what is required of us now. So for the common tangent to this ellipse and this parabola, then this, because it is common tangent, it means that it is the same line, so it will have the same equation, it will have the same slope. So then we can equate the slopes for each of them. So we will now analyze for the given ellipse. So for the ellipse, we are given the ellipse with equation, we are given this ellipse with equation. What is the equation of that ellipse? It is x squared over 6 plus y squared over 3 equals 1. So we're given this ellipse, which is x squared over 6 plus y squared over 3, y squared over 3 equals 1. So from this, we can tell that a, which is, if we try to put this in standard form, for instance, we know the standard form is x squared over a squared plus y squared over b squared equals 1. So if we want to do that here, this will be given by, or this will give us, so let's put that on this line. We'll have this to be x squared divided by the roots of 6 all squared, then plus y squared divided by the root of 3 all squared is equal to 1. So when we compare this, okay, we know root of 6 all squared will give us 6, so root of 3 all squared will give us 3. And when we compare this with the standard form, we now know that a for this ellipse is root of 6 and b is root of 3. So by that, we now say that therefore for the ellipse we have this to be a to be root of 6 and b is equal to the root of 3. So we can easily extract that from the equation as we just did. So what will be the equation of a tangent of slope m to the ellipse? So we now say that will now be given by, we just substitute here the values of a and b as required in this expression. So when we have that, we have our equation. So we now say that hence a tangent of slope m, a tangent of slope m to the ellipse, a tangent of slope m to the ellipse has the equation, so we expect that to be y equals mx plus or minus the root of a squared m squared plus b squared. So we now have a to be root 6, b to be root 3. So a squared is 6 and b squared is 3. So we now say therefore that is going to give us y equals mx, still there, m, we don't know what that slope is, that's what we're trying to find out now. And then this is going to be the square root of a squared. A squared is 6, so this is going to be 6m squared plus b squared. B squared is 3, so this is 6m squared plus 3. So this is the equation to the ellipse, sorry, of the tangent to the ellipse. So it tells us plus or minus, implying that there would be two of such tangents to the ellipse, okay, that can have this equation. Okay, so whatever we have here, we can have one that has the equation carrying plus, and we can have another that has the equation carrying minus. Okay, so let's keep this result and have that as say equation A. Then if we consider the parabola that we're given, the parabola is the parabola P, which is y squared equals 12x, then we will have that to be, so we're given also the parabola. So let's compare, let's see what that parabola gives us. It says y squared equals 12x. So if that is the case, we should put it in the standard form. When we try to put that in the standard form, we will have y squared equals, we want to put it as 4ax. So if we split this or factorize this will give us 4 times 3. So this is going to be y squared is equal to 4 into 3x. So when we compare this to the standard form of the equation, which is y squared equals 4ax, that means our a will be equal to, in this case, 3, because this is 4 multiplying 3 multiplying x. So by that, we will observe that a is equal to 3. Okay, comparing this with the standard form of the equation of a parabola, so a is equal to 3. So by that, we know that is the a that we will need here to get the equation of the tangent of slope m to the parabola. So we can now make use of that now. So therefore, so we now say hence the equation of the equation of the tangent of slope m, the equation of the tangent of slope m to the parabola of slope m to the parabola is given by so we have that equation up there. We saw that it was going to be equal to mx plus a over m. So we have that to be mx plus a over m. So we can now put that here. Our a is 3. So this is therefore going to give us the equation y equal to mx plus 3 over m. So this is the equation of the tangent to this parabola, which has the slope of m. So with this, we are good to go. We can now compare equations A and B. So if a given line, if the same line will be a tangent to the ellipse and also be a tangent to the parabola, then it must have the same equation and definitely it will have the same slope. So because of that, we can equate them. Of course, we have used m for both of them. We know that a here is different from the a here, so that's why we wrote out the equations separately. Okay, so we have used this expression. So if it is a common tangent to the hyperbola, sorry, to the parabola and the ellipse, then it must have the same equation. So we say that, okay, we now say for a common tangent, now say that for a common tangent to the ellipse and for a common tangent to the ellipse and parabola, equations A and B must be the same. So equations A and B must be the same. So it will give us the same results because it is the same line that touches both of them, and that is the meaning of common tangent. That means that tangent is common to both of them. So if that is the case, then we can equate the corresponding parts of these equations. So we can see that equation here we have y here, we have y here. We have mx here, we have mx here. So the part that we need to equate will be 3 over m and this plus or minus root 6m squared plus 3. So let us equate that. So we now say that therefore 3 over m must be equal to plus or minus root, what is that again? 6m squared plus 3. So this is going to be 6m squared plus 3. So that is that about that. So with this now, we're good to go. We can now solve this equation to see what the value of m should be for there to be a common tangent to the two to the two curves. So for us to solve this completely, we can square both sides so that we will get rid of this square root sign. So this is going to give us 9 over m squared equals 6m squared plus 3. And if we multiply through by m squared, this gives us 9 equals 6m to power 4, then plus this is going to give us 3m squared. All right, so we have this expression, and obviously 3 is common to everything here, so we can divide through by 3. This is going to give us 3 equals 2m squared, then plus, sorry, this is 3m to power 4, then plus m squared. So we will have to solve this equation. All right. So how do we go about this? We can tidy this up and say this is 2m to power 4 plus m squared, okay, minus 3 equals 0. So as we have it here, this is now a quadratic equation. For instance, we can say uh, let's p let's use p, or say let's use q to represent m squared, so that we now have this to be 2q squared, because the square of this, the square of q will be m to power 4, which is what we have here. So this will be plus q, okay, minus 3 equals 1. So we then solve this quadratic equation. So what is the solution to this quadratic equation? You can factorize this quadratic equation if you like. You can also use the formula method directly and all of that, but let us just go ahead and factorize this. We know 2 multiplying minus 3, that is minus 6. Okay, so when we put these two together, we can say this is 2q squared plus 3q minus 2q, then minus 3 equals 0. And from here, we can say this is q into 2q plus 3, then minus, that's all that this two have in common. So let's say minus 1 into 2q plus 3 is equal to 0. So from here, we have our q. So this is, when we factorize this is going to be q minus 1, okay, into 2q plus 3 equals 0. And from here, we will have our q to be equal to q is equal to 1, or 2q plus 3 is equal to, that is, q minus 1 equals 0. Let's write that out first. Q minus 1 equals 0, or 2q plus 3 equals 0. So with this, we'll have our expression to be q equals 1, or q equals minus 3 over 2. So those are the results we get from that. And of course, we know q is m squared. So this is telling us, this is suggesting that m squared equals 1. This is suggesting that m squared equals minus 3 over 2. Of course, we know that the square of a number, a real number that we are dealing with now, cannot be minus 3 over 2, cannot be negative. So that means we can discard this one. Okay, so we can discard this result, because the square cannot be minus or cannot be negative. So that means we now say that therefore m squared is actually equal to 1. And if m squared is equal to 1, that means m is equal to the square root of 1. Of course, what is square root of 1? That will be plus or minus 1. So that means m is equal to plus or minus 1. So that is that about that. So that means that the common tangent will have the slope plus 1 or minus 1. That tells us now very clearly that the two curves, that is the parabola and the ellipse, will have two tangents in common. One where m is plus 1, and another one where m is minus 1. So with this, we can now go ahead to get the equation of that tangent, for instance. Okay, so we know that the common tangent will be when m is equal to plus 1, and also when m is equal to minus 1. So with this, we are good to go. So the equation of that tangent will be, so we can substitute that into any of the two equations, A and B, because those two are equivalent, all right? So we can put that result here. So we have y equals mx plus 3 over m. So we now say that therefore the equation of the common tangent, thus the equation of the common tangent, the equation of the common tangent to both of these is, or the common tangent is, or we can say r, that is going to be y equal to mx. We have found m now to be plus or minus 1. So this will be plus or minus 1 times x, that is x, then plus 3 over m, that is going to be plus or minus 3 over m. This is 1. So we're going to have that to be y equal to plus or minus x, then plus or minus 3. So that is that about that. We have our results right now. We can now go ahead and simplify this. So when m is equal to plus 1, for instance, then we will have y to be equal to x plus 3. When x is equal to when m is equal to minus 1, we'll have minus x minus 3. Okay, so just substituting that directly in this expression, which is mx plus 3 over m, gives us that result that we need. So these are the two equations of the common tangent to the two curves. Okay, so with this, we can now go ahead and see what is required of us in the problem statement. Okay, so we have these two lines. We can, of course, have a sketch of these two lines. We can find out where these two lines actually meet each of the curves. Okay, and we can get literally every other thing that may be required. Okay, so this is the major thing that has to be done first. So we have now sorted that. Let's see how the rest would work. So let's go ahead and say that in this case, we have, for this portion, we say that the tangent T1 touches P and E at the point A1 and A2. So there are two tangents. So there is one we call T1, there's another one we call T2. All right. So there's another one, the T2 touches P and E, that's the parabola and ellipse at A4 and A3 respectively. So then which of the following statements is or are true? So let us have a sketch of all of this in a singular diagram now. That is the ellipse represented by this equation, the parabola represented by this equation, and those two tangents that we have now obtained their equations. We will put them all together in a single diagram so that we can visualize what is really playing out here. So let us draw that diagram here. Let's make that straight a bit. So we have this here and this here. So this is x-axis, this is y-axis. So for this, we have a to be root 6, as we saw earlier, for the ellipse, and b to be root 3. So we can make use of that information to draw or to sketch the ellipse here. So we're going to have something like this for the ellipse. So we have something like this for the ellipse, then like this, then we have this. Okay, that's it somehow, but you get the point. And this goes this way from here. So that is that. So along the x-axis, we have this to be root 6, that's plus root 6, and this will be minus root 6. And along this, we'll have this to be root 3, and this one will be minus root 3 right here. This is minus root 3. And then for our parabola, which is for which our a is equal to 3, as we have noted earlier, then we can also sketch that parabola. We know that it will be facing the x-axis, so we draw that to be, because a is positive and y is squared, we know that will be facing the x-axis, so we're going to draw that out here. So we have something like this for that parabola. Of course, the line can, but I mean, this can actually extend further like that. It can also spread out like this. Yes. So this is just some rough sketch so that we can visualize what is really playing out here. Then want to draw a common tangent. That means that it has to be tangent to this, for instance, so, and also be tangent to this curve. So we should have something that looks like this that touches the two curves. So let's redraw that. So let's say we have something like this that touches the two curves. Okay, it is tangent to both of them, and we're going to have that. Of course, we can spread that out here and see where it meets the x-axis, and then we can draw the same thing for the second tangent. We know that there will be also the possibility of having a tangent that comes here and then extends this way. Let's say that this goes here and then it extends this way so that it also meets this at a certain point around here. So let's say this is the point where this meets this is the point where this meets this. Okay, so where do the tangents meet the x-axis? That is when y is 0. So when y is 0, what do we get for this? When y is 0, we have this to give us x equal to -3. When y is 0 here, we will have x to also give us -3. So if y is 0, or what is that? Now, if y is 0 right here, we'll have x to be equal to -3. That is, if we set y to 0, we have 0 is equal to x plus 3. So this will give us -3. And if y happens to be 0 as well here, the same thing happens. We'll have this to be equal to minus x minus 3. So we'll move this to the other side. That's x is equal to -3 as well. So both of them will intersect at x equal to -3. So this point is actually -3. That's where these lines, this common tangent, meet the x-axis. Okay, so that is clear, that is settled. Then another thing we will have to bother ourselves about is where does this one meet this ellipse and where does this one meet this ellipse? Where does this one meet this parabola and where does this one meet this parabola? So those are the issues that we will now sort one after the other. So where does it meet the ellipse? That is another thing to have in mind. There's an expression also that tells us where that tangent of slope m meets the ellipse. Of course, we can always get that by solving the equation of the ellipse and that of the straight line simultaneously. But that will take a lot more time. Okay, so it is good if we already know what that expression is for the point where it meets the ellipse. That is, for that tangent of slope m, if we already know where it meets the ellipse, then we'll just use that expression directly so that we get the coordinates. So we need to get the coordinates of this point. Okay. So, but before we do that, let us quickly identify the points here as they have been labeled in the problem statement. The problem statement says that suppose tangent T1, so we're going to take one of them as T1. Of course, we should take the one that is positive as T1, and it touches P and E at points A1 and A2 respectively. So where it touches the parabola is A1, where it touches the ellipse is A2. So for the first one, where it touches the parabola is A1 and where it touches the ellipse is A2. So this is A1 and where it touches the ellipse is A2. So we can come back to find out what the coordinates of this point will be. Okay, so for now, let's just put in that label. Then for the next part of the problem statement, it says the tangent T2, so that's the second one, touches P and E at the points A4 and A3 respectively. So we will watch out for that as well. So the one that carries the negative sign, so we're taking where it touches the parabola to be A4, where it touches the ellipse to be A3. So A4 and A3. Where it touches this will be A4. Where it touches the parabola will be A4. So this is A4. So we'll come back to find out its coordinate. And this is A3. We'll come back to find out its coordinate. So it's such that this goes A1, A2, A3, A4, like that, in that order. Okay. So we should now find out what the coordinates of these points are. That is, where does this tangent of slope m, okay, meet the parabola, and where does it meet the ellipse? Where does this tangent of slope m also meet this parabola here and also the ellipse? Okay, so we know that this is the one that has slope. For this, m is equal to 1, and this is the one that has negative slope. M is equal to minus 1. So we now find out what the point of intersection will be with this ellipse and also with this parabola. So let's get back up here and see let's write out how that works here. So the equation of a tangent of slope m to the ellipse is given by this, and the point where it meets the ellipse, the point where it intercepts the ellipse, is given by, so this is the point plus or minus. So I'm going to write that out again like the first one without proof. If you are interested in how this works, you can let me know in the comment section so that we'll have a look at that in a separate video. So this is going to be given by a squared m squared then plus b squared, and for the y coordinates we have minus or plus b squared divided by the roots of a squared m squared plus b squared as well. So this is the point where this intercepts the where this tangent of slope m will actually meet or intercept the ellipse. So plus or minus means that this is plus or minus, this is minus or plus. It means that one will pick this positive, this is going to be negative. One will pick the negative here, this one will be the positive. Okay, so we'll come back to make use of that shortly. And in the case of the parabola, this tangent of slope m will intercept the parabola at the point a over m squared, and that's for the x coordinates, a over m squared, and the y coordinates will be 2a over m. So we just state that here without proof. Again, if you need me to show you how this came about, let me know in the comment section so that we'll have a separate video on that. But this may be too cumbersome. If it is for you to remember in the exam or for you to memorize, if you find it so, then you are still safe. What you should do is, having obtained this equation, like I said, that may take a lot more time to come about, but having obtained this equation, what you then need to do is solve this equation, okay, and that of the ellipse simultaneously. So when you solve them simultaneously, you see that's the point of intersection. Okay, and for the parabola also, solve the equation of the tangent and that of the parabola that we have just obtained, solve them simultaneously, and when you do that also, you will get the points where they intercept. Okay, and the reason for this is because we're starting off with the gradients and we don't have any option here. We have to start out with the gradients. Okay, so that is that about that. So let's go ahead and get what these coordinates will be, where these intercept the ellipse. So let's start with where it intercepts the ellipse. Those will be the coordinates of a2 and a3. Obviously, we know a2 corresponds to where y is positive, and in this case, x is negative for both of them. So it corresponds to where y is positive. So let's go ahead and see how that works. So we will come here and make use of this expression. We know this is the point of interest to us for the ellipse. This is the point of interest, plus or minus a squared m. So we know a squared is 6, b squared is 3. So we're going to make use of that expression right here. So let's see what that gives us. So for the coordinates, of what are those points now, a2 and a3, for the coordinates of a2 and a3, what do we have? We will have those points to be given by plus or minus the a squared m, as we wrote up there, divided by the root of a squared m squared plus b squared. Then we'll have minus or plus b squared into the roots of a squared m squared plus b squared. So let us see what that gives us now. We have our m already, so we know that our m is plus or minus 1, and in this case our a is equal to root 6, and so it's a squared that we need anyways. It's the square that we need, so let's write out the square directly. We know a squared is 6, and we know that b squared is 3, so we can put that those values here, and when we do that we get our result. So this is going to be equal to, we'll have this to be, for the x component, we'll have this to be a squared. A squared is 6 multiplying m. So let's pick when m is equal to 1. So this will be 6 multiplying 1. Then we'll have this to be the root of a squared, m squared, okay, plus b squared. So we need that on both sides. So let's just calculate that separately. The root of a squared m squared, we know that is the root of a squared, which is 6, okay, m squared, which is 1. So whether it is plus 1 or minus 1, that is going to be 1. Then multiply plus b squared. Our b squared is 3. So when we put this together, that will be the root of 9, which is 3. Of course, we know it's plus or minus 3, but we already have plus or minus 3 here. Okay, so we can just go ahead now and get the coordinates of this point. So we'll have this to be a squared m for the x coordinates, a squared m. That will be 6 multiplying this. So that will be 6 into plus or minus 1. So let's say 6 into 1, and then divided by 3. Then, comma, for this, we'll have 6 b squared, which is 3, then divided by 3. So what does this give us now? This is going to give us 6 over 3, which is 2, then comma 1. So we know this will be plus or minus, okay, plus or minus. But we can easily get whatever it's meant to be right here. If we look at A2, we know it is going to be around here. So, and in this portion that it is, our x is negative and y is positive. So that is what we will choose here. X is negative, so this is going to go with the negative, and then this will go with the positive. So that is the value that we seek. So this is going to be minus 2 comma 1. So what we have here, where it meets the ellipse, is going to be minus 2 comma 1. Okay, so that is that about that. And if you come here, as expected, when we put in minus 1, for instance, so let's say we ignore this sign for a moment, I'll put in minus 1. This will give us 6 into minus 1. So this will become the reverse of that. So we're going to have this thing here to be 6 into minus 1. We're going to have that to be minus 2. Then 3 will just be 3 over 3. Then that is going to be 1. But we know there is a plus or minus out here. So if we examine that, we know that in this case, our y is going to be negative and our x is also going to be negative. So we know this is meant to be minus 2 and minus 1, because in this portion x is negative and also y is negative. So that's how we choose the signs as we put them here. So this is like, we are not sure what the signs will be. We just know that this will be plus or minus, this will be minus or plus. Okay, so why are they now having the same sign here? They're having the same sign here because this one already has negative sign. From the fact that we're using minus 1, this already has negative sign. So if we put minus or plus here and then plus or minus here, we'll have exactly that. We'll have the same result at the end of the day. That is, we reverse the sign of one and choose to not reverse the sign of the other. So that is the point here. So if we reverse the sign of this, we know it will give us minus 1. And how do we know what exactly it should be? We just know from the sketch that this is meant to be, x is meant to be negative here, because this is the negative portion of for the x-axis. This is the negative portion for the y-axis. So this is minus 2 and minus 1. This is minus 2 and 1. All right, so we are done with that portion. And then looking at the expression for the where the tangent meets the parabola, we know that is at the points. Where did we write that again? Up here, a over m squared and then 2a over m. So that is quite easy to detect in this case. A over m squared and c over m, b over m, sorry. So that 2 over, what is it now? 2a over m. So this is for the coordinates of, so let's do that on a separate line anyways. For the coordinates of, so this was minus 2 and minus 1 that we eventually used. Then for the coordinates, of That's A3 and A4. I mean A1 and A4. So this is A1 and A4. A1 and A4. What do we have that to be? For the coordinates of A1 and A4, we'll have we'll have this expression up here, which is a over, where is that expression, a over m squared comma 2a over m. So we know that for each line we have the gradient up here to be m equal to 1, this one to be m equal to minus 1. So we're going to make use of that here. So we know that our coordinate is a over m squared comma 2a over m. Okay, 2a over m. And we know that m is equal to plus or minus 1. So when m is equal to, and our a, as we have it up there, is equal to 3 for the parabola. So when we put that here, then we're going to have 3 over m squared. M squared is 1. Whether it is plus 1 or minus 1, that's going to give us 1. Then 2a, that is 6, divided by m. So where m is 1, we're going to have this to be 6. So this is going to give us 3 comma 6, okay, for the first one, when m is equal to 1. And when m is equal to minus 1, this will give us a over m squared, which is still 3. Then 2a over m, that is 6 over minus 1. So this will be 6 divided by minus 1. And that will be giving us 3 comma minus 6 when m is equal to minus 1. So with this, we are good to go. We have 3 comma 6 and 3 comma minus 6. So which of them should go minus 6? Of course, this is a negative y portion. So this is going to be 3 comma minus 6, and this is going to be 3 comma 6. So that is that about that. So we can see that for both of them. So that means that this and this are on the same x coordinates. If we draw this line, this will be some vertical line, and the coordinate here is x equal to 3. Okay. And here, the coordinate here is x equal to minus 6, the coordinate here is x equal to 6. So with this, we are good to go. We have the coordinates of all the points, and we can now answer the question that follows. So it says the area of the quadrilateral A1, A2, A3, A4 is 35 square units. The area of the quadrilateral A1, A2, A3, A4 is 36 square units. Let's find out what that is going to be. So the first and foremost thing to observe here is the fact that the coordinates here also, x coordinates is minus 2, x coordinates is minus 2. So this is also going to be a vertical line. So as you can observe, it means then that this line is parallel to this line. Okay, so this is parallel to this. So what kind of quadrilateral would you call A1, A2, A3, A4? That is going to be a trapezium. So we can see this is parallel to this, and we can easily get what this distance is from this point to this point, because this is vertical and this is horizontal. So we can easily get this horizontal distance so that we can calculate the area that we need. Okay, so this distance also is easy to calculate. So we can just extract that trapezium out here so that we can easily visualize what its area would look like. So we're going to have something like this. That is the trapezium. Then this is one side of the trapezium, which is vertical. This is this distance right here. We can find that distance. Let's see what that distance is going to give us. And from, so it's just, this is simply the distance between this point and this point. Of course, we can calculate this using the formula for distance between 2 points, but that's going to take a long time. We just simply observe that the coordinate here is 6, the coordinate here is minus 6. That means distance from this center to this point is 6, distance from this center to this point is 6. So altogether, this distance is 12. So what we have here is distance of 12 units. Okay, and for this also we observe the same thing, that the distance from this point to this point is 1. That's the coordinate here. The distance from this point to this point is 1 as well. Okay, so that is addition of those, that will give us 2. And then for this also, the length from the origin to this point is, so we see the coordinate here is 2, so minus 2. So that means this distance from this point to this point is 2. So then the coordinate here we know is 3, so the distance from this point to this point is 5. So sorry, that is the distance from this point to this point is 3. Then the addition of both of them, that is 2. Distance from here to here is 2. then from plus this distance, which is 3, so everything here is 5. So this distance from this end to this end is 5. So we will insert that here. So that's what we have right here to be 5. And with this, we can now get the area of this trapezium. So A is basically going to be 1 over 2. That's the expression for, or the formula for getting the area, A plus B H, where A is one of the parallel sides, and B is the other parallel side. Then the perpendicular distance apart is what we call H. Okay, so by that we have this to be 1 over 2 into what is A? A, say 2, plus B, the other one, which is 12, then multiply by H, which is 5 in this case. So what do we have here? We'll have this to be 2 plus 12, which is 14. Then 14 divided by 2 is 7. Then 7 times 5 is 35. So this is 35 squared units. Like, so this is 35 squared units. So that is the area of the quadrilateral A1, A2, A3, A4. It is 35 square units. So with this, we are good to go. We can now answer the first question, or the first, we can now check for the correct option here. So the area of the quadrilateral is 35 squared units. That is true. And it says the area of the quadrilateral A1, A2, A3, A4 is 36 squared units. That is false. Okay. So it says the tangent T1 and T2 meet the x-axis at the point minus 3, comma 0. So where do they meet the x-axis? That was the first thing we sorted. This is x is minus 3, of course, and y is 0. So this is minus 3, comma 0. We have established that previously. And obviously that is true. Minus 3, x coordinate is minus 3, y coordinate is 0. Tangent T1 and T2 meet the x-axis at the point minus 6, comma 0. That is false. So we have now clearly established that options A and C are correct. So options A and C are the correct options here. So that's all about this problem. We've not solved it. We've come a long way. So the idea is that you understand the concepts behind this. It is not guaranteed that the questions will be repeated. So it is not advisable that you just learn the solution without actually getting the concepts behind them. So if you understand the concept behind them, then you know that whether the questions are repeated or modified or something entirely different is said, then you're confident that you are able to handle it. Okay, so that's what's important here. So if you find this useful, don't forget to like this video and subscribe to the channel, and also share this video with your friends who may be preparing for the same exam. So I'll see you in the next lesson as we take on the next problem. Thank you for watching.